Black holes are mysterious cosmic anomalies, the nature of which we are just beginning to understand. They are difficult to detect, and even more difficult to study. Space itself is distorted around these amazing objects beyond recognition, and the usual laws of physics become irreconcilable. Their study helps us better understand the deep essence of our universe, but at the same time it poses a certain threat. So how dangerous are black holes? Obviously, detecting a celestial body that absorbs all the light falling on it is a very difficult task. Therefore, there are currently not many confirmed black hole candidates known. However, mathematical modeling shows that in our galaxy their number could reach 100 million. This number seems huge, but when you consider that the Milky Way contains between 200 and 400 billion stars, it becomes obvious that black holes are quite rare objects. In one of the previous issues, we already found out that in order to become a black hole, the progenitor star must have a mass of at least 18 to 20 solar. Only in this case will the supernova explosion be strong enough to compress the hot core of the star into a superdense clot of matter. After this, nothing will be able to overcome the attraction of the object and leave the boundaries of the so-called Schwarzschild spheres. In place of the dead star, a mysterious object will remain, the internal structure of which can no longer be described by the laws of physics known to us. One of the closest black holes to Earth is an object called A0620, Diffeis 2.0, or V616. It is located about 3,400 light-years from Earth and is part of a double star in the constellation Monoceros. The second component of the system is an orange dwarf with a mass of about 50% of the Sun. Every 7.75 hours it makes a full revolution around an invisible object of unknown nature. Calculations show that the mass of this hidden celestial body is about 6.6 solar, which is too much for a neutron star. This means that the mysterious object is most likely a black rod. The attraction of a more massive neighbor not only deforms the star, giving it an elongated shape, but also tears off the outer layers of stellar matter from it. Swirling streams of hot gas gradually flow towards the black hole, forming a bright accretion disk, thanks to the radiance of which it was discovered. There are at least several dozen stars in the vicinity of V616, some of which most likely have their own planetary systems. It is likely that in the future one of these stars may come close to a black hole, resulting in the object being captured by the object's monstrous gravity. In this case, she will face the same fate as her current companion. The process of interaction of a black hole with other objects largely depends on the ratio of their masses. The smaller the distance between celestial bodies and the more massive the black hole, the stronger the tidal forces affect its companion. They can deform the star, pulling it towards the general center of mass of the system, and even form channels through which stellar matter will flow closer to the black hole, replenishing its accretion disk. If the tidal forces are strong enough, they can completely destroy the absorbed object and turn it into a ring of fire. It is assumed that, hypothetically, planets can orbit around a black hole, just like around an ordinary star. Contrary to popular belief, black holes do not have the ability to uncontrollably and inevitably draw into themselves all surrounding objects. From the point of view of gravity on a cosmic scale, they behave similarly to a star of the same mass, so a black hole may well have a stable planetary system. There are several possible ways of their formation. Firstly, the source of new celestial bodies can be a gas-dust nebula formed as a result of a supernova explosion. Under the influence of gravity, clumps of matter first form in it, which collide with each other and attract cosmic dust. As a result, planets and satellites are born, as well as many small celestial bodies such as asteroids and comets. In this case, the radiation from the hot accretion disk of the black hole may be enough to warm them and even melt the ice on the surface. Hypothetical similar planetary systems may be favorable for the origin of life. Secondly, when a black hole captures and destroys another planetary system, some objects in its composition can take stable orbits around a new owner. Of course, as a result of this process, conditions on the surface of celestial bodies can change radically. So, an ice giant can transform into an ocean planet, and a gas giant can lose almost all its hydrogen and turn into a chthonic planet. Thirdly, wandering celestial bodies such as orphan planets or interstellar spheroids will also be attracted by a massive object. And although such systems have not yet been reliably discovered, there are no prerequisites to consider them impossible. If the planet is located very close to the center of the system, and the black hole has sufficient mass, then other factors come into play. The hot flow of matter forming the accretion disk will strip the atmosphere from the celestial body. And friction will slow it down more and more, pulling it towards the black hole. Eventually, the strongest tidal forces will tear the planet into tiny pieces. The resulting fragments will continue to move in the accretion disk, gradually dissolving in the exhaust hot gas. In the end, they will inevitably be swallowed up by the black hole, becoming an integral part of it. It is believed that there are three main types of black holes in the universe, differing primarily in mass. The first type can be found at the center of most spiral galaxies. These are giant black holes whose masses can reach several billion solar masses. The density of matter in the central part of the galaxy is usually very high, which leads to the formation of a large number of closely spaced large and bright stars. Burning quickly, they turn into black holes, which grow rapidly and often merge with each other. As a result, supermassive objects are born surrounded by giant accretion disks consisting of hot matter. Their radiance can be seen from billions of light-years away, even if the galaxy itself is not visible at all. We call such objects quasars. The second type is much more common, but it is also much more difficult to notice. This includes black holes whose masses are close to stellar masses. They are formed from large stars at the end of their life cycle. By absorbing other celestial bodies and interstellar gases, these objects gradually grow, turning into intermediate mass black holes. They can also merge with each other, creating gravitational waves, distorting space for many light-years around. The third type is hypothetical primordial black holes. Their existence follows from the modern theory of the origin and evolution of the universe. Fluctuations and oscillations in matter resembling outer space in the early stages of its development could lead to the formation of black holes of arbitrarily small sizes. It is worth considering that according to calculations, the smaller an object of this type, the faster it evaporates at the end of its life cycle, turning into a powerful electromagnetic pulse. Modeling shows that primordial holes weighing about 10 to 12 kilograms should flare up around our time, but so far not a single such event has been recorded. In addition, there is a hypothesis that as a result of the collision of elementary particles of ultra-high energies, a microscopic black hole, also called a quantum one, can be formed. At the same time, the conditions necessary for such an event cannot yet be created in laboratory conditions, and the estimated lifetime of these hypothetical objects is so short that it is extremely difficult to measure it using modern methods. Therefore, quantum black holes are still only a hypothesis. Of course, detecting such dark and compact objects is quite difficult. Some of them have a stellar companion, the anomalous movement of which makes it possible to detect an invisible companion. Another common method is based on observing accretion disks. The spectra of such objects have characteristic features that make it possible to distinguish them from other cosmic light sources. In some cases, it is possible to obtain an image of a disk with a black spot inside, which proves the unusual structure of the observed object. Also, a black hole can be detected due to the effect of gravitational microlensing. To do this, a massive invisible object must pass between the Earth and a distant star, characteristically changing its spectrum. Obviously, the use of this method requires the coincidence of many rare factors. With all this, there is no doubt that space is filled with many dark and inconspicuous celestial bodies. Among them may be wandering black holes. Mysterious objects wandering in interstellar space and absorbing without leaving the slightest grain of light will most likely remain unknown to us.